Welcome to this video on transients on transmission lines. In this session, you will learn how faults affect power systems and how current behaves during these events. We will explore the different types of faults that can occur, understand the key differences between symmetrical and asymmetrical faults, and discuss the important assumptions you need to know before analyzing fault currents. I'll also guide you step by step through the derivation of fault current equation and explain the concept of doubling effect in simple terms. Let's get started. Transmission line faults can be caused by several factors. Some of them are trees falling on the lines, lightning strikes in transmission lines or substations, sometimes insulators may failure, and there are several other factors due to weather or contamination of some insulating material, some other regions. Now let us see types of faults. There are mainly two types of faults, symmetrical faults and asymmetrical faults. In symmetrical faults, all three phases are involved equally. The most common types are three-phase fault, also called LLL, which can occur due to substation busbar faults, construction accidents like crane contact with all three-phase conductors, or severe storms and cyclones. Another type is three-phase to ground fault, also known as LLLG. This happens when all three phases come in contact with the ground. This can be caused by earthquakes that lead to infrastructure collapse, flooding or substation submersion, or any maloperation such as forgetting to open an equipment maintenance earth switch. Another types of faults are asymmetrical faults. Asymmetrical faults involve one or two phases and are more common than symmetrical faults. These are single line to ground fault or SLG. It happens when one phase touches the ground. This is often caused by tree branches, insulator contamination from dust or salt, or animal and birds coming in contact with the conductor. Another type is line to line fault or LL. This occurs when two conductors touch each other. This can happen due to wind induced conductor clashing, failed insulators, or foreign objects like kites or some other material. Another one is double line to ground fault, also called LLG fault. This happens when two pairs contact the ground simultaneously. This is usually the result of lightning strikes, or pole or cross arm failure, or multiple insulators failure occurring together. This table shows how often different types of faults happen in power systems. The most common fault is the single line to ground fault, where just one phase touches the ground. This type occurs about 65 to 70% of the time and is asymmetrical. And another one is line to line faults, where two conductors touch each other, happens less often compared to LG. It is around 5 to 10%. A double line to ground fault involves two pages touching the ground together. This is more serious and occurs about 15 to 20% of the time. Finally, balanced or three-phase faults are the rarest, occurring only 2 to 5% of the time, but they are most dangerous because they can cause very high fault currents. Now, let us study transients on transmission lines. You may note that sudden load thrown off is not a fault, but it's a transient. We have to study these kind of situations when we do analysis of transient recovery voltages or switching over voltage studies. Now let us start the derivation of symmetrical fault current. Before we start analyzing symmetrical faults in a transmission line, there are some basic assumptions we make. First, we consider that all series resistances and reactances are combined together as lumped parameters. This makes the calculation easier. Second, we ignore the shunt capacitance of the line. This helps simplify the fault analysis without affecting accuracy much. You may get why shunt capacitance is neglected. There are few important reasons why we neglect shunt capacitance while calculating fault currents. During a fault, the system mainly behaves as an inductive network. High fault currents flow through the inductive parts like generators, transformers, and transmission lines. And another thing is the inductive reactance, which we call XL, is much higher than the capacitive reactance XC during a fault. By ignoring the shunt capacitance, we can simplify the equations and save time, especially when we do the calculations manually. In most cases, this does not create much error because the effect of capacitance is very small, especially in lines shorter than about 250 kilometers. Shunt capacitance also does not have much impact on fault current itself. The fault current mainly depends on the impedance of the source and the series impedance of the line. However, if we are studying very long transmission lines, let us take around 250 kilometers or more than that, or doing switching and over voltage studies, then the shunt capacitance becomes important and should be included in the analysis. Let's start by applying Kirchhoff voltage law to this simple RL circuit with a voltage source Vm sin omega t. What we get is Vm sin omega t is equal to R into I of t plus L into di by dt. This is a simple first order differential equation. Now we split the solution into two parts. First one is the steady state part, which is the AC current after transients die out, and the second part is the transient part, which is the DC offset current that decays over time due to presence of resistance in the circuit. The steady state solution looks like this. I steady state of t is equal to I max sin omega t minus phi, where I max is Vm by root r square plus x square and phi is inverse tan of x by r. To find the transient or DC offset part, let us solve the homogeneous equation, which is equal to L into di by dt plus R into I of t is equal to 0. We know that I transient of t is equal to A into e power minus t by tau, where tau is the time constant, which is equal to L by R. If we apply initial condition at t is equal to 0, the current must be 0 because the fault just has started. So I of 0 is equal to 0. Substituting t is equal to 0 into the expression, we get I max sin phi minus phi plus A is equal to 0. Then you get A is equal to I max sin phi. So if we write finally complete equation, I of t is equal to I max sin omega t minus phi plus I max sin phi into e power minus t by tau. The first term is the steady state AC current. The second term is the DC offset, which decays over time due to resistance. This is why right after the fault, the current can momentarily double and then gradually settles down. When we turn on the power or when fault happens, the current doesn't look like a normal smooth wave right away. At the start, the current is made of two parts. One part is usual AC wave that goes up and down, just it is a sinusoidal wave. The other part is called the DC offset. In this picture, you can see which is demarcated with pink line. This part starts high and slowly goes away. Because these two parts add together, the current jumps quickly and can be almost twice as big as normal. This big jump is called the doubling effect. After some time, the DC part dies out due to presence of resistance in the circuit and only normal sine wave remains. This is why the current shape looks a big at first and then settles into regular wave. Now let us discuss about doubling effect. The doubling effect refers to a condition where the current immediately after a fault on a transmission line becomes twice the normal peak current but only for a short time. This happens due to superimposition of steady state AC current and a transient DC offset, and both are in same direction. That is the reason why the current almost becomes double. This is called doubling effect. Let us study the doubling effect with two cases. First one is when R is present in the circuit, and second one is when R is equal to 0. Usually in 765 kV or 400 kV lines, for 100 kilometers, R is usually in the range of 2 to 3 ohms and X is in the range of 31 to 35, 36. Here I have taken R is equal to 2 and X is equal to 34 ohms. If you take R is equal to 2 and X is equal to 35, you will get phi as 86.72 and tau as 0.0557 seconds. And I did the same analysis. I of t is equal to I max sin omega t minus phi plus I max sin phi into e power t by tau. And at various angles, I calculated the output current. At 180 degrees from the table, you can see the I is almost 1.8463. It is almost double of I max. Here I max I have taken as 1 pu. You can see it is almost, it has become up to 80%, 180% of I max. This is one case. And second case is I have taken R as 0, means R is neglected compared to X. In this case, the same equation and the same derivation I did. If you see, in this case, time constant is infinity, because of which second term multiplication factor becomes 1, and the peak value at 180 degrees, the Imax is almost double the peak value. It is 2 pu. If Imax is taken as 1 pu, maximum current is 2 pu. And one more thing, you can see, if you observe the waveform, there is no decay in the circuit, and entire current waveform, entire sinusoidal waveform has been shifted to top part by I peak. In this, you can observe that why there is no decay of current. Why? Because there is no resistance, there is no damping in the circuit. That is the reason why current is, even though shifted by Imax, and it is maintained at that level. It will never come, it will never decay with respect to time. Symmetrical fault analysis is very important in power systems. First one is equipment sizing and selection. Circuit breakers, current transformers, relays, cables and transformers are all rated based on the maximum symmetrical fault current. This makes sure that equipment can safely withstand or interrupt the highest possible current without getting damaged. And another one is protection system coordination. Relays need to detect and isolate fault currents quickly and correctly. Accurate fault current calculations helps us set the relay pickup current and time delay properly, so that only the fault part is disconnected. Another one is ensuring system stability. High fault currents can cause voltage drops and make generators lose synchronism, leading to system collapse. Knowing the symmetrical fault current helps plan for better stability during disturbances. Another one is limiting damage and cost. If we over design the system, it becomes too expensive. At the same time, if we under design it, it becomes unsafe. So calculating the correct fault current helps balance cost and safety. And another one is for further studies. Symmetrical fault analysis is the starting point for all other important calculations like asymmetrical fault currents, transient stability studies, arc flash energy analysis, busbar design in substation or in various factories, earth grid sizing. In short, symmetrical fault analysis protects the system, ensures reliability and helps save money finally. Thanks for watching. If you found this video helpful, don't forget to like, subscribe and share it with your friends. If you get any doubts or feedback, feel free to write to me at mygatejourney@gmail.com. Your support keeps this channel growing. See you in next video. Thanks a lot.